All right. So let's first do the long division and then see how this one is gonna. I don't know. I think it is this one is flicking or something. I hope it's gonna settle. Sorry about that. All right. Okay, let's do the long division first. Exercise number 1. Use long division first. So I'm going to introduce synthetic division. Right, is that okay? The quotient is 2x squared minus x minus 3. The remainder is negative 4, right? So this is how the synthetic division goes. This is always linear divisors. So they don't want to play with this x squared and keep written down in here. They just want to play with a number of negative 3, 2, negative 7, and 0 and 5. They align the number and do this one quickly without writing down powers of x over and over. One thing they changed it might be confusing, is the following. But if you have this habit, you're not going to get confused. You write down the divisor. So this is synthetic division. I'm introducing it here. If you already know, great. You can just use that. If you don't know, maybe you're going to follow my suggestion. You write down x minus 3. That's a divisor, right? And you write down it's 0. What makes this one 0? 3 is a number. The plus 3. So plus 3 goes there, right? You write down a 0, and that's the method. And you write down something like this, like we did in the long division. And you copy down these coefficients, just a number. If it's skipping a term, you have to insert 0 in there, right? So it's a 2, negative 7, 0, and 5. Right? Then next thing they do is just, multiply and subtract. But because of the sign switch, they add. They don't subtract. The big difference in synthetic division is this number kind of switches the sign, and we don't subtract one row. It's actually always adding it together. Yes. All right. So the first step is that you have another line written here, and you just copy the very first number down here, 2. Nothing is happening to the first coefficient. Okay? Next one is that this one is written over here after some operation. You always multiply these 0 to that number. 0 to that number. So that's 6 there. Alright? But then how I got 6? I multiplied 3 to that number. So it's multiplication by 3 written there.
So you only write the constant?
Only deal with the numbers because they're all in place. It's going to be all written down in that fashion. So they eliminate this unnecessary part. As long as they are lined up like this, you know it came from which coefficient and so on.
What if there was a 2 in front of the x in the divisor?
Oh yeah, that's the next case I have prepared. I'm gonna let you know, but it is actually a tricky case. But right now, it's not only is a linear divisor, but it has a monic linear divisor. That means the coefficient of x is actually 1, right? So if it's not monic, how is this method going to apply? Which is the next example I prepared. Yeah. But right now, it is with a monic linear divisor. That's what Kelly pointed out. So are we going to subtract the 6 from the 7, or
Subtract.
this time we have to add? Because they flipped the sign. That's basically why. They flip the sign, so we don't subtract, but we just add. If you add this 2 number, that's negative 1, right? That's what's different from long division as well. All right. Then what is the next step we do? Multiply the 0 by 3, then you get negative 3. Is that right? Then you add this 2 number, get negative 3, right? And then you multiply that, divide your 3 again. That's negative 9, right? Now if you add this 2 number again, you get negative 4. So we got these 4 numbers, and I want you to look at long division in here and compare where they come from. 2, negative 1, and negative 3, and negative 4. Do you recognize all these numbers showed up in the long division?
Yes.
2 showed up in here, right? Negative 1 showed up in there. Negative 3 showed up in there, right? And negative 4 showed up in here, right? So that's the conclusion. That's the That's the coefficient of quotient. This is the remainder, right? So we started from degree 3, right? If you divide by linear, you always go down by 1. There's no exception. You only use synthetic division for linear divisor. You always go down by 1. So you start with a 2x 1 lower squared, right? Yes.
So what happens?
Divide those. We only do the division when the degree of a degree of a dividend is bigger than the degree of divisor. You can keep going for the fractions. Yes, there is a way to do that. Yeah, you can just keep multiplying 1 over something to knock down 1 at a time. But it's unending then, because you never end. And then it's kind of infinite series, and there's interesting mathematics toward to that part, what to do with that kind of thing. But we can keep going, but we stop it here with the lower degree. So if it's already lower, according to that algorithm, that's where we stop. But we can keep going. All right. So that's a 2x squared. What is the next coefficient? Next, negative x, right? And negative 3. And that's your quotient, right? And that's your remainder. And that's it. But we don't stop it. What is the last thing we do after all this division algorithm? You state division identity, right? Yeah, division identity. Let's do that. What's division identity here? First, we need to dividend. That's the whole thing is there. 2x cubed minus 7x squared plus 5 is now decomposed into x minus 3, right? Times the quotient, 2x squared minus x minus 3, remainder negative 4. This is an identity. So how many solutions are there to this equation? No matter what x is, infinitely many. That's correct. The number of solutions to this equation is infinitely many, not 3. Yeah. So that's why it's called identity. That's right. All right. So suppose we're lucky, we got this remainder 0 instead of negative 4, right? Then what this one becomes? This is now called division identity, right? If I have lucky and hit the remainder 0, and this is called, if it is 0, it looks like factorization. Yeah, this polynomial is factored into 2 things plus 0, right? So it's a factorization. So this synthetic division is used to factor polynomial out of it. If you're lucky, know what the factor is. Okay? Make sense? Great. 1. You want to do 31 or 32? Or 29? 28. No, I'm not going to pick 28. 32. Yeah, that's going to be exercise. Alright. Alright, this one, what are we going to say? Are we going to state division identity or the other one? And what is the other one? Division identity in quotient form. Remember that? Yeah. So this one is supposed to be written in quotient alone here, right? Plus the remainder. This time is our number divided by x minus 2. This is our goal, right? But I want you to use synthetic division. You got the quotient? This is called division identity in quotient form. Exercise number, what was 1? Oh, the long division, that's right. How was it? Yeah, because I everybody likes it, of course. But this is a final answer, right? Don't stop here. This is a final answer. You have to understand this meaning of the equal symbol. That's identity. We want to pull out identity. That's what's important in mathematics. Yes. Any other question? That's fair enough. So I think I have this example of using synthetic division of 3x plus 2, right? 3x plus 2.
Wouldn't you just take the 0 as it is?
Right, that's the same thing. And we're going to just do it as like we did it before. And at the end, when you put it into a division identity, then you can rearrange it. Oh, this means that, therefore I have what I want, and things like that. So let's begin together and interpret it. Yeah, it's in part an exercise. So we can call this an exercise number 3. Thank you. So here's a divisor, right? 3x plus 2. And what do? Write down the 0. Right, not 2/3. Negative 2/3, right? You set that equal to 0, and that's the number you have there, right? Correct, 2/3? Any question? You set that equal to 0. You set that equal to 0, and what is the x? That number goes there. That's the meaning of 0. A number that makes this polynomial 0. Then what did we do? We copied down these numbers. What is that? 3, 5, 5, 2. None of this missing, right? If it's missing a term, you have to put 0 in there, right? So I want you to finish the synthetic division for that setting. It's the same thing. All right? So that's your exercise 3. Do the synthetic division there. At the end, we're going to interpret it correctly later. I think it was fairly quick, right? Right? And it's something that I think you were afraid, oh, 3 down there and it's going to get ugly, but it always cancels 3 and give you a nice number, right? All right, very good. So here's the thing. If you look at this synthetic division, if it has mind, the synthetic division does not know where your divisor was x plus 2 over 3 or 3x plus 2. Because they have the same 0, correct? If I divide this polynomial by x plus 2 over 3, you will have exactly the same result, correct? Because it doesn't know, just this part doesn't know where it came from. It has the same 0. So actual conclusion is that this is actually the polynomial 3x squared plus 3x plus 3, right? With remainder 0, with that divisor. That's the answer. So let me write that down. So from there, the conclusion is that this 3x cubed plus 5x squared plus 5x plus 2 with the which divisor? X plus 2 over 3, not 3x plus 2, had a quotient 3x squared and 3x plus 3 and remainder 0. So it became a factorization. So that's the division identity associated with this synthetic division. Yes. All right, what synthetic division allow you to conclude is this, right? So synthetic division only works for monic linear divisor. Synthetic division is not allowing you to do that. So synthetic division only allowing the monic divisor, right? That's why it works like this. But that's not what we want, right? What we want is instead of x plus 2 over 3, we want to have 3x plus 2 instead of that. Right. Yeah. Exactly. But if you multiply 3 left-hand side, that's going to change the left-hand side, right? But we're going to keep the left-hand side. So that's the dilemma in here, right? But there's something free, something amazing happening in that quotient. What is it? 3 is always there. It is an interesting mathematical theorem that if you do that and treating as if it came from here, you will always have the common factor you want. It's guaranteed by mathematical theory. There will be always this number there for you, so you can factor it out. All right? Now I'm factoring that out. 3 out there, right? Then it's x squared plus x plus 1. Is that right? What are you going to do with that 3? Yeah, put that in here. Then it's now 3x plus 2 is multiplied by x squared plus x plus 1. There it is. That's the synthetic division. Well, that's too much. Then you do long division. Alright? Then you will get this one really quickly. If this part is too confusing, and then this is the correct answer. The final answer should be this. Yeah. That's the divisor, and that's the quotient. So use the synthetic division to state the division identity. If it is like this, non-monic, it involves two more steps. But if you practice a couple more times, then I can put that 3 right there, and you can go from here to straight easily after you practice a couple times. All right? So here is your one time. Exercise 4. So see if you can go from the synthetic division to division identity straight without writing that down and doing that algebra. Once you understand, you don't have to repeat that. It's the same thing there. So see if you can go from here, that information, to straight to the division identity. You will see, there's a number I want, right? Because the 3 disappeared, you want that. I want 3 there, right? And you will see that there is guaranteed that you will see the 3, and you can put that 3. You can factor out that 3, and that's your quotient. Good luck. Nice method, isn't it?
Yes.
Yeah. What did he say? Like, please clap or something? All right. Any question? Synthetic division. So, but let me go back and emphasize that only for a linear divisor. If it's not, then you can't use it. You have to go back to long division. Question? Kevin? No? Just checking the wall? All right. Right. Now, like the last 2 examples, it's about factoring. We're using the synthetic division mostly to factor out linear factor. So let's think about this factoring and factor theorem. So yeah, I want you to go and try this one. It's just a challenging exercise. It's about the terminology 0. What is a 0 of this polynomial?
We get 2 zeros, 2 different zeros.
No, what does x
Right.
have to be to make it?
Exactly, that's what a 0 is. Yeah, what is the number that if you plug it in here, this polynomial becomes 0? 2 works? I don't think it 2 works. Well, exercise number 5. Okay, there it is. Came back. Yeah, if you couldn't find this simple number, it's an ugly number. It's hidden. It's not there for you. So how do you find that ugly number? Quadratic formula. Those 2 numbers that make this one 0 happen to be ugly like this. Not 1/4, 1/2, 3, 2. All right? Any question? Times negative b plus minus square root of b squared minus 4ac all over 2 times a, where that's a coefficient a, that's coefficient b, and that's coefficient c. Correct? Yeah. Okay. Maybe it's a second challenging exercise. And do you know how to factor this polynomial? So that's your exercise number 6. Factor this polynomial. So what goes inside there? 1 and 1? If you expand it, it's not that. What are these numbers in there? Suppose if I have 5 and 11, how do you check this is wrong? Yeah, plug in x equals what? 5 in here. What happens if you plug in x equals 5 there? Whole thing is 0, right? But what about left-hand side here? You tried, some of us probably tried 5. It wasn't 0. So this is incorrect. There shouldn't be 5, right? There shouldn't be 5.
It should be 17/4.
17/4, something like that? Yeah? Anyone else? whatever is in here, that number, if you plug in the same number here, that must be 0. Also it showed up as a number that makes this whole thing 0, right? Does that make sense? So whatever that goes in here, that must be the number. If you plug it in here, becomes 0. What are those numbers?
1 plus square root of 17.
Thank you. It's 1 plus square root of 17 divided by 4. If I plug in that number in here, obviously this is 0, right? I just showed that, calculated that. This is one of the numbers that makes the left-hand side 0. So what is the other one then? 1 minus square root of 17 divided by 4. Right? That's one ugly factorization.
How did you know to take 2 out?
That's right. So if you don't have 2 there, it matches zeros there, right? It matches the 0, but it does not match the leading coefficient. So by throwing that number, you match the leading coefficient. It seems like just a game to match certain information. Right. It doesn't look like I showed it algebraically, perfectly to show it to you this thing is actually correct. It seems like I'm just clinging on to a couple of information and then I'm claiming that now they must be the same. It seems like that, right? Right. That's why it's called factor theorem. Because of that gap, it is called a theorem. All right? If you happen to have zeros, you can collect it as a linear factors here, right? And then just to match the coefficient. If you have enough number of zeros. So that's a theorem. That's called the factor theorem, pretty much. All right?
Sure, whatever you say.
Right. But now I'm explaining why that works, that understanding that you didn't have in here. So for example, so I'm going to call that one alpha. I'm going to call that one beta, right?
No more Greek, please.
Yeah. So here is the long division. We're not actually doing the long division, but think about it as a more qualitatively. It has 2x squared, x minus 2. If you divide this one by x minus alpha, right? There will be a quotient. We're not actually doing the long division. Think about long division is always possible, right? Whatever you divide a degree, as long as degree is greater than or equal to, you can always do that, and there will be always a quotient, and there will be always a remainder, right? That remainder here is a number, because of this is a linear divisor, right? So if you actually divide this polynomial with this ugly coefficient, you will see there's an ugly quotient, and there's a remainder which is pretty. What is that remainder supposed to be? 0, because if you plug in alpha here and alpha there, we know it's supposed to be 0. So there's an ugly qx sitting there, but there's a pretty r, 0 there, right? So here's a 2x squared minus x minus 2 and x minus alpha. And because the factor showed up and everywhere, if you divide x minus beta as well, right? And that this must have x minus beta in there. This is called unique factorization of polynomials. So qx must, if I divide qx, right? So here, if I divide qx, this must have x minus beta in there because it doesn't have x minus alpha in there, right? So I'm going to call q tilde x, and the pretty coefficient here is 0. And this qx has now linear, right?
Yes.
If I divide linear by another linear, this is supposed to be constant now. Degree go down by 1, quotient. So this one is x minus beta times the qx now is a constant. So I'm going to call that one just a c plus 0. So it became the c times x minus alpha, x minus beta. What did that c have to be? That must match the leading coefficient that we had before. Therefore, it must be 2 times x minus alpha, x minus beta. Right. So if you happen to have 0, 2 zeros, write down those x minus 1 0, x minus another 0, and match the leading coefficient, and that's a full factorization. This was explained through long division in qualitative version of long division. Not actually calculating, but looking at the shape, it goes down one at a time. All right. So that's factor theorem. It says if you have a 0, that x minus c is a factor in there. Okay? If x minus c is a factor, it's really easy to understand why that c is a 0. Right? So let me copy that statement and challenge you one more time to explain one part of the factor theorem. If c is a 0, only easy part, if x minus c is a factor, c is a 0. Is a 0. So it's because proof px, the polynomial, x minus c is a factor, then x minus c times qx. That's it, right? That's the meaning of x minus c being a factor. So why is x equals c equals 0 is if p of c, if you plug in c equal there, the c, and whatever that q thing is multiplied by 0, so it's a 0, right? So I showed that x equals c is a 0. Now let's look at the other way. This is interesting part. If c is a 0, then x minus c is a factor. This is something that you use all the time. I'm challenging you to explain it. Why is x minus c is a factor? Because of what result we recently looked at.
Because if C makes one of the factors 0, you have n equals 0.
So that's pretty much just reciting this one. What was the actual reason that explained x minus c appeared as a factor? The only thing that we learned here is long division. It's a long division. Here's a proof. If you divide px by x minus c there, right? Then there will be a remainder, and there will be a constant quotient and constant remainder, and this is division identity, right? This is going to always work. All you have to show is why r is 0. So how do you show is r is 0? If you plug in x equals c into this polynomial we have a condition that is a 0. Therefore, it's supposed to be 0. That's left-hand side, right? But what is happening on the right-hand side? Right-hand side, if you plug in x equals 0, is 0 times qc plus r, right? So only r survives. But these two things must be equal to each other. This is identity, right? But left-hand side is a 0. Right-hand side is r. That says r must be 0. So if you do the long division, if c is a 0, we prove that the remainder must be 0. Therefore, the polynomial px is x minus c times the quotient, and remainder we just argued it's a 0. Therefore, x minus c is a factor. So to show c is a 0 and x minus c is a factor actually requires this algorithm and understanding that algorithm always work. No matter what c is, no matter what qx there is, this division identity is always there for us in this shape. Okay. And we use it all the time freely, right? X is 0 is a factor. The factor is a 0. Now we don't think about this at all. So now we use a factor theorem. But if somebody in the guy in the street asks you, why does this factor theorem work? And that's because of the long division. Because of the long division and all that. That's a one-liner answer. All right?
Because I said so.
All right, I think that's the next thing I want to do. All right. So let's do this nice exercise.
So 7.
Yeah, the last one plus 1, which is 7. 0 and factor is the same thing. And it's unique factorization. Always, there's no two ways to do it. It's always one way to do that, right? That's unique factorization. There's some serious theorem behind this. All right. It has two things, I think. Px, x cubed minus 7x plus 6. First part, 1 point, show that p of 1 is 0. Yeah, you plug it in and verify it, and that's all that is. Yeah, yeah. But use this this fact to factor px completely. Factor px completely. All right. So let's do this part together. P of 1 is 1 cubed, right? Minus 7 times 1 plus 6. You checked multiple times, and it was sure it was 0. So we've done that. So how do we translate this one? What is the meaning of this one? P1 equals 0. Then you say x equals 1 is a 0. That's the immediate thing, right? But we just had a factor theorem, correct? So what it says, x minus 1 is a factor of which polynomial? Px over there. So if it is a factor, can you factor that out? How do you do that? Right. What method are you going to use? Synthetic division. Because x minus 1. Yeah. That's the... So also, after you do that, think about this completely part. See if you can actually do the completely. All right? How nice the synthetic division is to allow you to. So don't be stubborn here. If you don't get 0 in here, you gotta fix it. It's supposed to be 0 if you have a 0 in there, right? So you realize, oh, that's a 0. Now I'm going to do the division, and oh, you turn out to 5, and then you just cross it out and keep going, and that's wrong. Any question about this problem? Right? So actual question is that how can you find that number 1 there, right? If you have a 0, then you can factor that out. But how do we find a 0? That's the main question. And that's very unsatisfactory answer to that. All right, let me see. All right, so let me introduce now rational zero theorem. Okay, so first, so what are rational numbers? How do you understand rational numbers? Integers are rational number, but there are more rational numbers that are not integers. Anyone else? We often say square root 2 is not a rational number, something like that. Yeah. What's that? Whole numbers, but there are more rational numbers that are not whole numbers. Right, fractions, correct. Right. So, rational numbers in mathematics is defined to be quotient of two integers or whole numbers. That's a rational number. All right? 17 divided by 137, that's a rational number. For polynomial, there are 3 possibilities. Please understand the 3 possibilities, and the whole strategy will make sense. Sometimes it only had rational zeros. We just saw in the one ugly example that 2 of them are both irrational zeros, right? With the square root 17? Yeah. But some polynomial has some rational zeros and some irrational zeros. All this thing happens. So something called rational zero theorem only helps us to find these rational zeros. If there is irrational zeros, it's going to be very difficult to find. And there are whole loads of a PhD study developed to take care of this, studying these irrational zeros. So we only focus in these rational zeros. That is simple. All right? So irrational zero is hard. Rational zero is not that hard. And how to find the rational zero is not efficient. It is very inefficient. So we only focus on degree 3 and 4 and simple cases just to understand the idea. Yes? All right? I think I'm supposed to show rational zero theorem. Let's read this together and Try to make sense out of it. So here's a statement, and I'm going to copy that statement and kind of simplify it for degree 3 and degree 4 if this notation is too much. Let me see. All right, rational zero theorem. The polynomial, let's say it's degree 4, is the first coefficient, leading coefficient. I'm going to call it a4, x to the 4th power. Next one, x to the 3rd power. I'm going to call the coefficient a subscript 3. And a2, x to the 2nd, a1, x, the constant a0. All right? It may have rational 0, it may not have rational 0. Everything it had may be irrational 0. Maybe it does not have rational 0 at all, just like an only imaginary. But if there is a rational 0, that must be in that form, right? One integer divided by another integer, such that if you have common factors, you can get rid of the common factor, right? Why would you write like that if it's simpler form? So this is called in the lowest term. When you write down rational number, we usually say it's in the lowest term. So that if that's so, then if the rational zeros if there are rational zeros there, it looks like that, and p came from a factor of a0. That's what it says, right? This is an integer. P came from factor of a0, and q came from factor of leading coefficient. And if there's ever a rational 0, it must be in that list. So this gives you candidates to check if it is actually 0 or not. So think about how you do the quadratic case. Quadratic case, you juggle these numbers of integer factors, right? This is a generalization of what you do when you factor quadratic polynomials, actually. Okay? So numerator came from where? Constant term. Numerator came from constant term, and denominator came from leading coefficient. All the integer factors, including plus minus signs, right? But if you have two signs together, they're combined into one sign, right? So you can put the sign always in the numerator. Let's see if I have an example of doing that with the quadratic. Great. Here's the rational zero theorem example. You already know how to factor this polynomial, right? You already know how to find the rational 0 by factoring it. But we're going to just go by this one and get used to it. All right, so that's called the rational zero theorem. All right, let's use first one in here. Let's do this as an example. So if there's ever rational zeros, it is coming from leading coefficient and the constant is about p divided by q, right? So I want you to write down on all the p's. P is coming from where? Constant term, right? So is it plus minus 1? Is that integer factor? Plus minus 2 doesn't work, right? 3 works, right? 3 doesn't work. 5 works? 5 works. And 7 works. And 35 works, right? This is it. This is the only integer that divides the 35. And q must come from in here, right? But 1 is the only. We don't assign sign in here because if you combine it, always plus minus is all in there. So q is not doing anything in here, right? So you have to check how many numbers? 1, 2, 3, 4. So 8 numbers. Brute force search. You plug it in until you hit 0 out of this 8 number. That's what this method is. Yes. So you have to consider both sign for p. Okay, so what is the answer here? Was that x equal negative 5 and 7? No, I think it's a positive and a negative 7, right? These are the two numbers. It actually works, right? Because it factors it's plus. No, that's right, right. This is how it factors. Yeah, yeah. All right, but we're not factoring. We're pretending that we actually brute force plug in a 5 and plug in negative 5 and 2 until you hit that 5 in here. All right. So one might plug in all this number. Another might, oh, this list is long. So once I hit the first time in this list, you're going to hit this positive 5, right? So suppose you didn't hit that number, 7, but you hit it. I got 1. What is the efficient way to find the next one? Synthetic division. Rather than keep trying this, could be long number, right? Rather than keep trying, maybe you're going to factor it out, right? If it is not long, then that you can try it, but maybe synthetic division is better. So I suggest you, rather than just keep trying this number, once you hit one number, go ahead and do the synthetic division. So why don't I make that one an exercise? What? Yes. What's your question?
So how, like on the Hilberton, how far?
Right. There's no way that I'm going to ask you to do the brute force search that is hidden in somewhere in the middle. So can you do the synthetic division in here for this one and make that on exercise 8 or 9? Use synthetic division to factor. Factor out x minus 5. Is that right?
Yes.
X minus 5. That's 0 and factors that. Alright. I think this helps you understand this factoring procedure of a quadratic even better with this division algorithm actually. Any question about this factorization? Alright, so we just factored quadratic polynomial with a difficult method. Alright? But it can be generalized to a high degree. Alright. I think we already did that. Let's try this one. Yes, exercise 9. What's different this time? Right. 2 is in there, so Q is going to have a list in there. So what are the list of P? 1 and negative 1. That's very fortunate. 1 and negative 1. How about Q? 1 is a possibility. There's no plus minus for Q. 1 or 2. That's it, right? That's the only factor. So let's list the candidates. Candidates. So there's 1 and 2. If you have to multiply number in that P list and number in that is 1 times 2, right? So total of 1 times 2 candidates. And always plus minus in there. So basically, it's plus minus 1. And what is the next one? If you combine with that 2, 2 goes to denominator, right? So it has to be plus minus 1 over 2. Right? So this number goes to denominator. So if you have longer lists, you have to combine all of them, 1 in the denominator, 1 in the numerator. No, it has to be the divisor of 2 in there. You have to combine these two. Where did the 4 come from?
I mean, like plus 1, minus 1, plus 1 half, minus 1 half.
Yeah. Oh, the 4. That's right. So that's correct. The 4 candidates, but without plus minus, you're gonna write down these 2 slots with a plus minus. So together it's 4. So you have to try these 4 numbers, right? So suppose, pretend we tried all that. What is the first number it hit? X equals. It hits 1, and then you do the same thing, synthetic division, and factor it out and all that, right? Okay? So this is a mainly exercise about listing this one in here. Okay? It's slightly different from the earlier list. So even if it gets long, then in the test problem, you're going to hit early on. But the rule is that first, write down all the integers. Try integers first, right? And then none of the integers work, then try the fractional part with a smaller denominator, right? So I should prepare this problem in the test so that you hit it early on, not trying that. Okay. So I guess idea is clear. Fair enough. All right. Let's go and actually try this guy. So that was open exercise. We did it together. Give Give yourself 1 point or 2. Here's number 10. All right. First, this is the problem. First part is that list the candidates. For rational zeros. We're going to list them, but they're not all 0. You have to test them, right? So which one's 0 and which one's not. Right? Is that okay? P is coming from all the integer factors of constant. So it could be plus minus 1, it could be plus minus 2. And that's it, right? Q is coming from 1, so 1 is the only thing. Right? So number 2, why don't you list all the I'm going to continue. It's not all. These are just P and Q, right? So if you combine them all, because Q is 1, the answer is plus minus 1 and plus minus 2. Is that right? Now from the list in part 2 and find the 0. Find a rational 0. Rational 0. These 4 are only candidate, right? If there's ever a rational 0, it must be one of those 4. Go ahead and try and figure out which one is. Oh, it's pretty easy, right? Find a rational 0, x equals 1. X equals 1 worked, right? That's a rational number, correct? So what's number 3 is going to be? Yeah, factor out which factor? Factor out x minus 1, right? X equals 0, that's a 0. Then x minus 1 must be a factor. So factor that out. See what you get. So that's number 3. Right, if you factor out x minus 1 using synthetic division, you have x squared plus x minus 2 as remaining factor, right? And you realize that you can actually factor that quadratic again, right? So here, x cubed minus 3x plus 2 is equal to x minus 1. And this one factors x plus 2, x minus 1, right? Okay? So whenever you see the same factor, we call it multiple factor or multiple 0, you write it like this: x minus 1 raised to second power and x plus 2. All right? So that's usually how the factorization is written. If there's a common factor, you have to write it into an exponential form. So this is complete factorization of degree 3 polynomial using rational 0 theorem, right? But you may end up at this part being not factorable, right? So here's a final remark. Suppose you have some cubic polynomial and you did all that rational 0 theorem brute force search and you end up at x plus 1 and x squared plus 1, like that. Suppose you end up like that, right? So can you factor this one further? That's imaginary number. If it factors further to a real number like that, it allows to have a real 0, right? But this does not have real 0. No real number, if you square it and add 1, became 0. It's a positive number plus 1. It will never hit 0. So it cannot be factored like this. If it factors, it corresponds to real 0. So it is irreducible. This is the term called irreducible. So this is considered as a complete factorization. You can't do anything further, right? Yeah. Fair enough? How about this guy? X squared plus x plus 1. This is completely factored. You have to look at it here, think about how to factor, right? How do you factor this one? Quadratic formula. And what's going to happen if you do the quadratic formula? B squared minus 4ac. That's a negative number, right? then you're going to have irrational imaginary number. So factored or not? Right, it's a complete factor. It's irreducible. Why is it irreducible? Right, inside the quadratic formula, b squared minus 4ac, called discriminant of this quadratic polynomial, is a negative number. Then you know immediately it's irreducible. You don't have to factor further. If this is a positive, then there might be ugly factorization. Remember that? 4 plus root 17. It might have that ugly factorization. If it is less than 0, it cannot be factored. So that's a quick criterion you can go through, wishing that is a negative. Alright. Course evaluation is open.